Good afternoon and welcome to the Using Magnetic Separation to Improve Commodity Recovery webinar. I am your organizer, Michelle Beacom, the managing editor of CIM Magazine, and my co-organizer is Ryan Bergen,
hello,
editor-in-chief of CIM Magazine. Our panelists presenting today are Aaron Powell of the Saskatchewan Research Council and Jane Denoxy of SRC Mining and Energy Division. Just a little housekeeping before we get started. Oh, shoot. Where's my slide presentation thing? Just a little housekeeping before we get started. To ensure you have optimal audio, please make sure that you have the computer audio button selected. And if you're joining by phone, please make sure that you have the phone call button selected. We will have a question period at the end of the webinar. You can type in your questions in the question box that you can see on your dashboard, and the presenters will answer questions at the end of the webinar. Now, without further ado, we will turn it over to our presenters, Aaron Powell and Jane Denoxy. And I will do that right now. Thank you.
All right, thank you very much, Michelle. I will.
How'd that go?
Okay. So thank you for the lovely introduction, Michelle. As Michelle mentioned, my name is Aaron Powell, and I manage the process development team here at the Saskatchewan Research Council. And I'm going to start by giving a little bit of an introduction into the Saskatchewan Research Council and our newly expanded mining and energy services. And then Jane Denoxy will share her expertise in magnetic separation with us. So the Saskatchewan Research Council is one of Canada's leading providers of research and development and technology commercialization. SRC's mining and energy team provides services that meet industry needs across the mining cycle for a wide range of commodities, including diamonds, uranium, potash, lithium, base metals, precious metals, and rare earth elements. SRC provides technological solutions and testing while considering social and environmental impacts from exploration and design feasibility to operations and closure. So SRC's newly merged Mining and Energy Division continues to provide world-class services in geoanalytical and mineralogical services, and as well as expertise in process development. So we continue to offer applied diamond services, minerals processes, tailings, process design and optimization expertise. However, this combines into a newly expanded service line when combined with existing services under energy. So biological and catalytic processes, energy optimization and integration, greenhouse gas emissions reduction and modeling. And this allows us to provide expertise across the entire mining cycle. As many of you may already be familiar with, we do continue to offer the same world-class service you're already aware of. So geoanalytical laboratories, applied diamond services. We are internationally recognized for secure and reliable micro and macro diamond recovery and are ISO 17025-2005 accredited. We're on the forefront of developing and applying innovative solutions in diamond exploration, such as caustic fusion and process testing. Our research scientists and process engineers continue to bridge the gap between research and industry. And we also provide diamond characterization and advanced processing, including nitrogen typing, grading and damage breakage of diamonds, ore and gangue luminescence studies, plant design, and mine auditing. And with the merger of mining and energy, we've actually got some expanded service lines, where our world-class diamond expertise combines with our expertise in process design, energy optimization, and greenhouse gas emissions reductions. So we do work in process design and process optimization for mine operations, and in greenhouse gas emissions reductions under our Center for the Demonstration of Emissions Reductions, also known as CEDAR. Now, there are three routes to greenhouse gas emissions reductions. The first one is energy optimization of processes and facilities. The second is energy replacement with alternative and renewable sources. And thirdly, there are direct emission reduction implementation. An SRC can support technology selection for this type of implementation. We also have a database of over 350 emissions reduction technologies with comparative data to allow in technology selection. We can support real-world field testing of technologies. And one specific example of emissions reduction that is novel is carbon capture and storage in kimberlite tailings. So there are many minerals processes available, and these start from comminution and beneficiation, physical separation techniques such as magnetic, which we're going to talk about in a minute, density and hydrophobicity, chemical separation techniques such as leaching, solvent extraction and precipitation, heat separation, solid-liquid separation, and hydrotransport of slurries. And the goal here is really, ideally you want to maximize separation as early as possible going through these processes so you can optimize operation and reduce costs. So I will now turn the presentation over to Jane, and she will discuss how magnetic separation can be used to optimize sorting and process design.
Thank you, Erin. Okay, I've decided to do this magnetic separation discussion is because I do feel that magnetic separation is underutilized in most mineral processing plants. So in this presentation, I'm just going to start off with the introduction, then classify the different magnetic minerals as they appear in textbooks and as you actually relate to them. Then I'm just going to mention a couple of ideas of how magnetism is used in exploration. We're going to look at magnetic sorters, and then at the different magnetic fields the magnetic sorters generate. We're going to look at the ore, its magnetic properties, specifically magnetic susceptibility. Then I'm going to just show you how magnetic traces are useful in setting up equipment, as well as setting up magnetic separators. We're going to look at a flow sheet design and actually interrogate it for where we could actually utilize magnetic separation, and then finally give a summary on the discussion. So when classifying magnetic minerals, we all hear about iron and cobalt being very magnetic, but they're actually different classifications of magnetism. Strongly magnetic minerals are called either ferromagnetic or ferrimagnetic. It just depends on the different magnetic domains in their structure. But the big difference between ferro and ferri is the fact that the Curie point is a little bit lower in the ferrimagnetic minerals. The Curie point is the temperature at which the material loses all of its magnetism. So here, what we're talking about is magnetic susceptibility psi, or that X, is very high for ferro and ferrimagnetic minerals. Paramagnetic minerals have much lower psi, a couple of orders of magnitude lower than ferro and ferri, and often they are overlooked, but they are very valuable. If you do have very strong magnets, you can start utilizing these paramagnetic properties for sorting, and it offers opportunities to the mineral processing industry. Then the last category that I'm just going to mention is diamagnetic minerals, and these are minerals that have negative psi or are actually repelled by a magnet. So the force is no longer attraction but repulsion, and minerals that are typical of this are quartz, calcite, and diamond. So now you've got the range of different magnetic classifications that are going to be used throughout this presentation. I mentioned about in surveys, when you're surveying for different minerals. When you are doing magnetic surveys, that's a flyover in the aircraft, and you're looking at the signatures of the Earth and the crust and all the different magnetic differences, on the screen is typical of what you would see. Now, but when you're looking for kimberlite, kimberlite is weakly magnetic, and it also is found in volcanic pipes, which usually have a carrot-like shape within the Earth's crust. So these small differences in magnetic characteristics between the magnetic kimberlite and the surrounding country rock are seen as small little dots on an area survey. So what you see here is the first little signatures of kimberlite. Again, with another filter, you're seeing these kimberlite signatures again. And here you're actually seeing the kimberlite signatures quite easily. But all of these signatures come from that little square. So you've really got to zoom in and actually have a look for these small perturbations on a magnetic survey. But the reason why we can see the kimberlite is because it has magnetic properties that are different from the country rock. What I'm just showing you here is a flow sheet design for an iron ore concentrate. And in the process of recovering iron ore, magnetic separation is used quite intensively. So we've got a coarse process here and a fines process on this side. But what I wanted you to see that before you go, okay, I've got all the acronyms here as to what they are. So LIMS is a low intensity magnetic separator. MIMS is a medium intensity. W stands for wet, and HIMS is for high intensity magnetic separator. So the WIMS is a wet high intensity magnetic separator. But what you see in the flow sheet, which is very important, is that your low magnetic separator comes before any high magnetic separator, because you want to pull off your ferrous material that will stick, and you wouldn't be able to get it off of a high magnetic separator. So it's very important that there is always a LIMS before a HIMS. Moving on and looking at some magnetic sorters or applications for magnetic separation in your processing plant. I think people will recognize the first picture on the left being an overband magnet, just pulling off trump iron off of a belt before it goes into your plant and starts doing damage to your equipment. Very important to have one of those up front. Then on the right, I've got a 3-stage magnetic separator. And what you would have, like I just discussed, your lower magnetic separator will be on top, your MIMS will be in the bottom, and your HIMS will be, okay, MIMS will be in the middle and your HIMS will be at the bottom. So you would have like 4 fractions of magnetic material, from very magnetic ferrous material coming off your top magnet to paramagnetic material coming off of your bottom magnet. Then on the bottom left, I've got an example of a wet high intensity magnetic separator, used often to recover ferrosilicon in our diamond plants. And on the bottom right is a metal detector, also used to remove and recover metal trump iron on a plant. At the SRC, this is the magnetic equipment that we use quite extensively. The first one you've seen before in the other picture, but this is just a single stage magnetic separator, very broadband magnet. It's around about 2 feet across, so it has quite a high throughput. And due to different belt speeds, we can set up different cut points. Then on the right, we have the perm roll. And what's nice about this laboratory perm roll, although it does small batches, is that the actual magnetic roll here is replaceable. So we can replace this with either a high intensity magnetic roll or a low intensity magnetic roll, depending on the client's requirements. And then at the bottom here, we've got a France bridge that we use for the smaller minerals. And what's advantageous about the France bridge is that it runs on an electromagnet, which means that we can vary the field and vary the magnetic separation cut point depending on the current that we actually run the machine at. So just verifying, this is the laboratory perm roll. This is the hopper. Material goes into the hopper and onto the feeder. The function of the feeder is to ensure that the material is in a monolayer. Then the belt is run at a much higher speed, and that's to spread it out so there's no impingement and no minerals are touching each other. so that every mineral that goes over the magnetic separator and the magnetic field is able to experience the full field, the magnetic field, without any touching or impingement from an associated or an adjacent mineral. Goes over the magnetic field and into the two fractions. There's a splitter plate in here behind this iron shield, and then the mags get pulled towards the magnet and into the mag fraction, whereas the non-mag material isn't affected by the magnetic field and goes into the non-mag fraction. Here is the short movie on how the perm roll operates. On the feeder I've got here is a mixture of almandine and a non-magnetic quartz. So monolayer on the feeder, going onto the belt, being separated, then coming through over the magnetic separator and into your two fractions, your magnetic fraction and your non-magnetic fraction. And as you can see now, you can start seeing the color differences between the almandine, the magnetic almandine, and the non-magnetic quartz. Here we have the France bridge, which also mentioned we're going to be sorting the similar kind of sand particles on it. There is the feeder, and it comes, okay, the hopper coming onto the feeder. Here is the magnetic field, and what you see on this plate here is two chutes. The top chute is going to be affected by the magnetic field, where the bottom chute is not affected by the bottom field. But as it comes past the magnetic field, the magnetism will hold the materials to the top chute, while the non-magnetic material will drop out under gravity into the bottom chute. And as it comes to the end here, you will see that the two bins, the magnetic bin, the top bin, and the non-magnetic bin, the bottom bin. And here's the video of, so here is just a picture of the material being fed into the France bridge. That is on the hopper onto the feeder, and it's now that the feeder feeds it onto the chute, and now you can see the two chutes. And what you can see underneath here is a magnetic almandine being held in that magnetic field, and now you can see the two separation, the magnetic almandine and the non-magnetic quartz.
Great, very interesting, Jane. Now we have time for a poll. We're going to launch a poll right now.
Okay, Michelle, thanks.
We're just going to let it stay open for a couple minutes for everybody to vote, or a minute, not a couple.
Yeah, just a minute.
Okay, I'm going to close the poll now and share the results. So you can see, oh, we have pretty even laboratory and process plant, and the other two much lower. Thank you very much, and back to you, Jane.
Thank you, Michelle. Okay, moving on. So we are seeing how magnetic separators work, but do we understand the field, the magnetic field surrounding the magnetic separators? And it is important to actually understand the field configuration for you to actually choose the right magnetic separator for your task at hand. So here I've got just a schematic of a perm roll magnetic separator. And you know, on your perm roll, you usually got discs of magnets, and they are configured north and south, then south and north, and then north and south and north. So you know that like poles repel. So there's a big push away between all of these disc magnets. And to actually construct this, they put, okay, spaces in between these different magnets, as well as really strong bolts to actually bolt the magnets together. And what this does, it generates a magnetic field with the kind of field lines that I'm trying to draw here. So when field lines are close together, you've got strong magnetic fields. When field lines are far apart, you've got weak magnetic fields. So you can see round about your spaces is where your fields are going to be the strongest. But you can see that the field actually varies right along the axis of your magnet. And one way to actually analyze the field for a magnetic separator is to use cylindrical coordinates. And what I use is the Z coordinate in a cylindrical coordinates is how your magnetic field varies for a disk configured magnetic separator. So here you can just see the almandine and quartz going over the magnetic separator. You can see the discs here with the little spaces in between. So that's how they are configured on a magnetic separator. I've taken out the roll on our magnetic separator so that you can also see how the different disc magnets are configured. We all know that in a magnet you have your north and your south, and that's how your field lines are actually configured. But now when they're all configured, when the disc magnets are placed together, you're getting this configuration. So you're shorting out the long magnetic fields, and now you've got short magnetic fields. So you can see that they all come down round about the position of the spacers. Another image, so there's all your discs of your magnets, and you'll see that your spacers are actually quite important because they actually dictate the gradient of your field. So they either squeeze down your field lines or they are able to elongate your field lines. So depending on your configuration, your spacers and your magnets are all very important. If you've got large magnets, you're going to have large dead zones along your magnetic separator. So that was the one configuration. I'm going to move on to another configuration where you've got axial magnets, and the magnets are placed along the axis of your cylindrical magnetic separator. And again, we've got the south-north, north-south, south-north, north-south. So this generates this kind of magnetic field around the theta position of your cylindrical coordinates. So now it no longer varies along the Z coordinate, but along the theta coordinate. And here's just a schematic of how the rod magnets will be configured in the drum. And now these will be static, and what actually moves is the shell around it. And then the shell around it will pick up your material, it'll be separated. Whatever is magnetic will adhere to the drum and be pushed over to the magnetic side, whereas the non-magnetic material will be pushed out to the non-magnetic region of the separator. Okay, so we've spoken about the theta coordinate and we've spoken about the Z coordinate. The R coordinate, what happens when you move radially away from your magnetic separator? That is your gradient. So what we see here is this depends on the size of your particle you want to separate. So if you've got a large particle, say 4 millimeters, say this dot is around about, say 2 meters off the cylindrical magnetic separator, then your particle, we analyze our particle at the midpoint of that particle. So this will be looking at where your 4 point will be separating, and you can see that your magnetic field has already dropped practically to half. So if you've got a particle of 10 millimeters, this point here is at 5 millimeters radial position, so this is the midpoint of a 10 millimeter particle, your magnetic field gradient now is under a quarter of the strength of what it was at the surface. So the gradient is also very important to monitor and to realize. And as I showed you in the previous picture, that is a function of your spacers and how you configure your magnetic separator. Here's a Gauss meter, and this is kind of like the instrument that you would use for looking at your gradient as you move in the radial direction from your magnetic separator. What I've got here is a very strong, the neodymium boron iron magnetic separator is a very strong rare earth magnetic separator. They're both very strong at the surface, although this one is the 7.71 is stronger than the 5.5 rare earth magnetic separator. But what's interesting is when you get to around about a 4 millimeter particle, they both seem to have the same magnetic field separation capabilities. And when you get to a 10 millimeter particle, the weaker magnetic separator actually has the better gradient and actually is able to separate slightly better than the stronger one due to the gradient of its field. So these are just some of the aspects that you should bear in mind when looking at magnetic separators. At the SRC, we've also got the 2-stage magnetic separator for our plant. Okay, similar to the 3-stage, but only 2 stages here. So you would typically have the stronger magnet at the top, the weaker magnet at the top to separate your ferrous material, and the stronger magnet at the bottom to separate your paramagnetic material once your ferrous material has been removed. Here's an example of a wet magnetic separator, and most people in the plant know that we use this for recovering our ferrosilicon and recycling it. Ferrosilicon can be quite expensive, and it does minimize your operational costs on a plant. The coal plants usually have magnetite, and they use the same kind of operation. And there we can see the ferrosilicon being pulled up by the wet magnet and over into the bin where it is then recycled through the plant.
Okay, now we're going to have our second poll question. I'll just give a few more seconds.
Thanks, Michelle.
Okay, I'm going to close the poll now. And there are the results. And back to you, Jane.
Thank you, Michelle. Well, looking at the magnetic characteristics of the ore, to do this, we actually use something called a magnetic susceptibility meter. And this tells you how susceptible a particle is to magnetization. So what I've actually got here is an image of a magnetic susceptibility meter that I actually chose. And I chose this instrument, the KLY5, because it's one of the few, if not the only magnetic susceptibility meter that actually measures diamagnetism. Lots of instruments measure paramagnetism and ferromagnetism, but this instrument measures all the different categories, included diamagnetism, which is your negative magnetic susceptibility. I'm going to talk about the importance of measuring your magnetic susceptibility, but the other aspect of magnetism is also your hysteresis. So I just want to mention about what the hysteresis curve is. So I'm just going to start off with this diagram first on the left. When you magnetize a mineral, first of all, it starts to creep up as you increase your field, so your magnetism increases until it saturates, till everything is magnetized and it doesn't have any more magnetism left in it, and that's your saturation point. Then what happens when you want to remove that magnetism, you reverse your magnetic field, and then what happens is it slowly returns. But when your magnetic field has been reduced to 0, you will find that you've still got a remnant magnetic field in your particle. And you see this typically with pins if you do any sewing, and you'll see that if you drop some pins and you pick them up with a magnet and you pull the pins off the magnet, your pins will still stick together. There are little magnets in their own rights, and that is called their retentivity. And to actually remove that magnetism in the pins, you would have to reverse that magnetic field even further. to a point, and that's called its coercivity. So the amount of force that you have to apply in the reverse direction gives you the coercivity of your magnetic mineral. Now, why is this important? Okay, what I've shown here is a hysteresis curve or something with a large remnant magnetism. And this is actually very important when you are recording memory devices, you know, like typically in computers and things. But anyway, what I've got here is something with a very strong remnant field, a moderate remnant field, and a small remnant field. Why this is important to the mineral processing industry is that when you actually recover your ferrosilicon, what you saw in the wet magnetic separator, if you don't demagnetize, that also has a remnant magnetization. And if you don't degauss it, then what I've got showing here is a degaussing meter. Then you find that when it goes into your magnetic separator, your cyclone, that it actually increases the viscosity and you don't get as good as a separation in your magnetic separator. So you actually want to make sure that all of your ferrous material in your medium is actually demagnetized. So your rheology and your viscosity is minimized. But going back to susceptibility, we understand now your hysteresis. Your susceptibility is when your material starts from neutral and is first subjected to your magnetic field. Then your magnetic susceptibility is your tangent to your magnetization at that point. So that gives you the magnetic susceptibility reading, which is what I capture in my Kappa bridge. What I've done here is actually looked at a parcel of diamonds. The parcel of diamonds was typical of what is recovered from a recovery plant and was a selection of both gem diamonds. There were some brown diamonds in it, as well as some included diamonds. I've drawn a red line here to show you where your zero magnetic susceptibility is. Diamonds are diamagnetic unless they have inclusions, and if the inclusions are paramagnetic, it will actually influence their characteristics and move it over to the diamagnetic, to the paramagnetic area. So we've got paramagnetic minerals on this side and your diamagnetic diamonds on this side. And after I've done all the characterization, we looked at what was now a viable point to set on our magnetic separator so that we could recover all of our valuable diamonds. So some of these diamonds here will be classified as more industrial and of not as valuable as your gem diamonds. And this is just an image of the gem diamonds that were measured. And you can see color doesn't make a difference. And there is a couple of inclusions in here, but these diamonds were all diamagnetic and were all safely recovered if we use a cut point of around about 2 × 10⁻⁷ CGS, magnetic susceptibilities. All right, so we know what our cut point is from our Kappa bridge, from our magnetic susceptibility measurements of what we want to set our magnetic separator. So what do we do to actually set this point on our perm roll? So what I've got here is traces. We've got traces here of different magnetic susceptibilities, a 10, 20, 40, 60, 80, etc. We identified that we wanted 20 × 10⁻⁶. This is in CGS. That was 2 × 10⁻⁷ in the previous graph. So we want to cut somewhere in here. So we would want all of these traces reporting to the non-mags, these traces reporting to the mags, and these traces split hopefully 50-50. And what these traces do is they act just like density tracers. I trust you are familiar with density tracers, and they help you determine your D50 and your cut point, but from a magnetic perspective. Similarly, you can do the same thing for ferromagnetic minerals. When you want a different cut point, we know we've got 2 passes on that one magnetic separator at the SRC. So the first magnetic separator, we would use more ferromagnetic tracers, whereas on the second pass, we would use our paramagnetic tracers. So depending on where you just set it up very similarly. What I've got here is partition curves for magnetic separation. I trust many of you haven't ever seen partition curves for magnetic separators, but it's very similar to density partition curves. And what you can see is here, I've got my 20 susceptibility traces, and here I was able to recover 40% to the non-mags and lost 60% to the lost 60% to the non-mags and recovered 40% in the mags. Here 80% were recovered in the non-mags, and so on. You can see your D50 is round about 12 susceptibilities. And so you can see at different belt speeds, your belt speed dictates where your cut point is. As you increase your belt speed, so you increase your D50 or your cut point. And with this, you can set up your partition curves and see exactly where your magnetic separator is cutting. Going back to the flow sheet for the iron ore, so all of these separators, you could set up your cut point specifically and identify where it is just using the magnetic tracers, passing them over, counting them, and seeing exactly where the D50 is, just like you would do for a density separation method. So just looking at the flow sheet design, what we want to look at is to determine all the areas where magnetic separation can be used. And secondly, we want to determine where magnetic separation could be useful. They're not always the same thing. Here I've got a flow sheet courtesy of Multitech, and I just want to critique it with you. So first of all, up front here, I've done a beige cross. We all know that before putting material from a stockpile into a plant, we would put an overband magnet, and this would to remove the trompe iron. I've made the more yellow crosses for where we would actually put up a magnetic separator. Often we saw in the diagrams where I was doing the area survey that there are magnetic differences between the kimberlite and the country rock. They could be exploited with a magnetic separator so that you are not putting barren rock through your plant. And if you don't put your magnetic separator, remove your barren rock up the front with a magnetic separator, you definitely want to remove the barren rock before your HPGR, because your high pressure grinding roll doesn't often like the harder country rock, and that does destroy your chevrons as well as reduce your life of your HPGR. So you've got two areas that you could think about exploiting magnetic separation to remove your country rock. Again, I've got an orange cross for a overband magnet. There's a stockpile here, and often trompe iron gets thrown onto a stockpile. You do not want trompe iron going into your DMS circuit because it will create havoc. So there is the overband magnet positioned on prior to going through the DMS. DMS, you saw a wet magnetic separator. We need one there, and it's shown here for recycling your ferrosilicon and to reduce your OPEX costs on your plants. So there's another application. Then we know that what comes off of our DMS is the heavies. The minerals that are heavy are often magnetic. Magnetic minerals are usually much heavier than your paramagnetic or your diamagnetic minerals. So here we might put in another magnetic separator, and we can concentrate our diamondiferous material even further. We can actually concentrate that by 50, even 60%. And that would actually reduce the amount of equipment we need in our final recovery. In our final recovery, we're often looking at X-ray machines, grease machines, maybe some laser amounts, those finer high-tech equipment. And if we can reduce our material by 50%, that means we can cut our equipment in our recovery area by 50%. So big financial savings from that perspective. And lastly, you can look at your material that you give to your hand sorters. You always use your hand sorters for your final verification that your diamond is 100% diamond in your diamond parcel. But they have found that if you actually do a separation on your included stones and your non-included stones, that you get far more efficiency out of your sorters. It's more easier to pick included stones from a concentrate that's got paramagnetic minerals and your gem diamonds from a concentrate that's just got non-magnetic minerals. So that helps with your efficiency of your final sorting. So operational considerations. From the start, I was telling you, you need a monolayer, as well as it's spread out so there's no impingement and no touching of associated minerals. The other aspect which I haven't mentioned is a limited size fraction. You want a 1 to 2 size fraction in volume so you can actually get a better magnetic field for the application. You saw with the gradients, you're going to have a various gradient on your magnetic separator. So you want to make sure that your gradient is minimized, your variation, your gradient is minimized, and you do that by limiting your size fraction that's going over your magnetic separator. And the other aspect that I've been mentioning to you over and over is a tiered process. Your weak magnetic separator up front, and then your medium separator second, and your strong magnetic separator last. You have to have a tiered process. So in summary, magnetic differences are useful and need to be exploited by the processing industry. However, you do need to understand the configuration of your magnetic separator so that you can choose the right technology or the right configuration of your magnets for the application. Very important. Weak magnetic separation first, followed by a strong magnetic separator. It's also very valuable to actually characterize your ore with a magnetic susceptibility meter. And if you are looking at diamagnetic properties of your ore, like in the diamond industry, then the copper bridge, it might be the instrument that you need to start to utilize. And then I've just given you some ideas on how to evaluate your flow sheet to optimize where magnetic separation can be used. Is it viable to use in those areas? Is there differences between your country rock and your kimberlite that showing magnetic properties that can be utilized? Thank you. Over to you, Michelle, for question period.
All right. Thank you very much, Jane. So just a reminder to everyone, in your webinar control panel, there's a field for you to type your questions in, so we can get to them. I do have a few here for you. Can the magnetic configuration of a magnetic separator be checked without a Gauss meter?
It can be checked without a Gauss meter if you've got magnetic traces. So as you saw, you've got different magnetic susceptibilities on your traces, and if you utilize them over your magnetic separator and do your counting like you would do in a dense medium separator with density traces, you can draw up your partition curve and see exactly where your D50 and where how your magnetic separator performs for the different susceptibilities that you're interested in.
Thank you. So a magnetic separator is classified as a bulk sorter, but could a particle sorter be used instead of a magnetic separator?
I wouldn't use the magnetic separator as a particle sorter. It is a bulk sorter. You are subjecting your minerals to a magnetic field, a bulk magnetic field, and it is specifically designed for bulk sorting. Very similar to the DMS. The DMS is also a bulk sorter. So you can see, like with the partition curves and the traces, that's how you would analyze, a bulk sorter.
Thank you. And can the magnetic characteristics of an ore be characterized without a magnetic susceptibility meter?
It can at times if you've got an idea of what ballpark your magnetic characteristics are in. You can use your magnetic separator that you've set up with your traces and see which magnetic tracer your minerals report with. And knowing the trajectory and watching the trajectory and knowing which whether it's in the magnetic fraction or the non-magnetic fraction, and how it reports with the magnetic traces, you can get a good idea of your minerals susceptibilities, magnetic susceptibilities.
Thank you. So at what point you showed a separator removing almandine from an exploration sample. Could you explain that briefly?
Okay, so the almandine is magnetic, where the quartzitic sand is non-magnetic. So as soon as the almandine gets subjected to the magnetic field, it will be influenced by the magnetic field. So typically report to the magnetic fraction, whereas the quartz, which is non-magnetic fraction, isn't influenced at all by the magnet and reports to the non-magnetic bin or the non-magnetic fraction.
Okay, thank you. Well, if I don't know if anyone has any more questions, but that's all in the lineup right now. So, Michelle?
Oh, we have another question.
Oh, all right. Thank you. So it was shown a design with 3 stages for magnets, one for the weakest, ferro, and one for the strongest one, paramagnetic. What about the one that is in the middle?
So if you saw the big range of ferromagnetic minerals. So if you've got a large range of magnetism in your ore body, then you might want to do 2 stages for your ferromagnetic minerals. Because as soon your steel and everything will actually adhere to your magnet. So one of the things you could do is actually speed up the belt on the top one as well to actually push off your really magnetic particles, and then the middle one you would get off your moderately magnetic particles, and then you can look at your paramagnetic particles and do fine magnetic sorting on your paramagnetic particles with a very strong magnet.
Great. Thanks.
Well, it looks like we've run out of questions, so I think we'll end the webinar now. I really like to thank Aaron Powell and Jane Denoxy for this wonderful webinar, and we hope that you will join us for the next one. It's on the screen there, Wednesday, I don't know actually what day it is, sorry, December 11th, 2019 at noon Eastern Standard Time. We will be sending you a survey at the end of the webinar. Please fill it out. We'd really like to know your thoughts on the webinar. And you'll receive a recording of the webinar in a few hours this afternoon. And in the recording email, there is an invitation for the final diamond webinar, using diamond typing to improve recovery techniques. Anyway, thank you very much, Jane and Aaron, and thank you to all our attendees. Goodbye.
Thank you.
Thank you.
Bye.
Bye.